All right, hi everyone, my name is Anisha. I am a second year PhD student in the Material Science and Engineering department here at Northwestern. So how many of you have ever drank water out of a plastic water bottle? Probably most people. What do you do with that bottle once you're done with it? You probably throw it in the recycling bin. Now, how many of you have ever cooked using a spatula or made ice cubes out of a really flexible ice cube tray? Now, what tends to happen to these products once we're done with them? Say you can't use them, maybe there's a rip in them, or they're just not functioning as you need them to anymore. Well, most traditional curbside recycling programs will not accept these, meaning that they usually end up being tossed in the garbage. Now, why is that the case? Well, it's due to the materials that are in those products. So a lot of these spatulas and flexible ice cube trays are made of what are known as silicones. So silicones are molecules that are composed of silicon and oxygen atoms in addition to several other elements such as carbon and hydrogen. They're really known for their really good heat resistance as well as their flexibility, making them versatile and used in many different applications ranging from cooking to medical devices to sealants and adhesives. However, as mentioned earlier, these are pretty difficult to recycle compared to other plastics. Now, why is that an issue? Well, when manufacturing silicones, a lot of energy and natural resources go into them. Additionally, most of them just end up being incinerated, which leaves a really big carbon footprint. And of course, the ones that are just thrown in the landfill end up kind of staying in the environment for decades without being able to degrade. So why is it the case that silicones are difficult to recycle while other plastics can be more easily recycled? Well, if we look at the structure of these different materials, we can get an idea of why that's the case. So silicones and plastics are all made up of what are known as polymers. Now, polymers are long chains of repeating units. You can kind of think of them as beads. Now, many different polymers fall within two very broad categories. The first category are known as thermoplastics. So you can find thermoplastics in things like your plastic water bottle, your grocery bag, or the plastic utensils you get with your takeout food. Now, these types of thermoplastics can actually melt when you add heat to them, meaning that once you are done with these products, they can be reformed into a new shape, essentially being recycled. And now, why is that the case? It kind of helps if we understand the structure of these thermoplastics. So these thermoplastics are composed of these long polymer chains, and once some heat is applied to them, those chains can now move freely past one another, allowing for the thermoplastic to be reformed into a new shape. Now, the second category of polymers are known as thermosetting polymers. You can find these in things like your car tire, melamine dishes, as well as the silicone spatulas in your kitchen. Now, unlike the thermoplastics, these thermosetting polymers can actually not really be melted down. They're kind of like baking a cake. Once you have set them in a certain shape, they cannot be changed. So why is that the case? If you look at their structures again, they're composed of those polymer chains, but a secondary component is added to these. These permanent bridging molecules are added so that all of those individual polymer chains are actually connected to each other. It kind of becomes like a net, meaning that even once some heat is applied, those permanent bridges keep all the chains connected to each other so they can't really move past one another, making it difficult to reform into a new shape and essentially rendering these thermosetting polymers unrecyclable. Now, can we do better? Is it possible to do something to the structure of these thermosetting polymers, and in particular silicones, to make them a little bit easier to recycle? So in my work, I am starting out with these silicones, but instead of adding these black permanent bridges, I'm replacing them with these dynamic bridges. And what these dynamic bridges can actually do is once some heat is applied to this silicone, those dynamic bridges can cut in half so that these polymer chains can now more easily move past each other like they can for thermoplastics. So what if we want a dynamic silicone that has some different characteristics? Depending on the application you're using it in, you might want a silicone that's stronger or more flexible. For example, if you have an ice cube tray, you probably want something that's pretty flexible and soft so that it's easy to take out those really hard ice cubes from it. Whereas if you're wearing a smartwatch around your wrist, you probably want something that's a little bit more durable and strong and more resistant to everyday wear and tear. So what we found in the lab is that if we start out with this dynamic silicone and add in some extra ingredients that contain some amount of those permanent bridges, we can actually come up with a material that is now tougher, stronger, and more resistant to harsh chemicals. However, this silicone that we have now, its structure gets changed by those additives. It no longer really behaves like that dynamic silicone and ends up behaving more like a traditional thermoset, making it hard to reform again, making it difficult to recycle. So the big question now is, can we have both of these different characteristics while maintaining some amount of recyclability? And that is what I'm trying to understand in my research. By really understanding the structure of these dynamic silicones and how the structure changes by adding in different additives, I'm trying to understand what the trade-off looks like between those desirable characteristics, such as having a stronger and tougher silicone while maintaining some amount of recyclability. And hopefully, one day down the road, some of the insights that we're gaining from making these silicones in the lab scale can be applied to everyday household silicone applications. Thank you.